So as I have mentioned, we are trying to solve a computer vision problem here using PyTorch. It will be a multi-class classification problem. So the modules will be required: torch vision that contains the dataset, your model architectures, and image transformation, not just yeah, image transformations for your computer vision problem. That's torch vision. Then we are going to use dot datasets module. There you will find many computer vision datasets for a range of problem that contains your classification, detection, segmentation, video classification. Okay, then we are going to use torch vision dot models section that will contain well performing and commonly used computer vision model architectures implemented in PyTorch. Okay, then we are going to use the transforms, dataset, and data loader, and these three are the main focus basically of this tutorial, so that you can understand how to use data loader. And the data loader will use the iterator. Basically, data loader is nothing but a iterator on top of this data set, and data set uses the transforms to transform the tensor to the reliable format that your deep learning machines can understand. And these three are the main building blocks of building any PyTorch pipeline for your machine learning or deep learning solutions. So we'll go through it. Okay, and here as you can see, the torch.utils.data.dataset and torch.utils.data.dataloader classes are not only for computer vision problems. It can be rolled out to any problems. You have structured data, unstructured data. Let's say you have documents data or text data, data from Excel, CSV. There also you can use this one. Okay, so at the very beginning, we have some basic imports, okay, to do for this one. So let's just do the imports very quickly. So we are going to import torch. Let me just create a replica of this one. Okay, so we are going to import here torch and neural network module from torch, then torch vision. Then we are going to import datasets from torch vision. Then as mentioned, right, we are going to use some of the functions of transforms module. So from there we are going to use datasets, two tensors we are going to use from transforms. Okay, and I think it's double two times same thing. Okay, and once that's done, we are just importing matplotlib for some plotting purpose. And once that is done, we are just printing the different versions. Okay, so let's just run this cell. So all the imports can not going to use any custom dataset. We are going to use a fashion MNIST dataset readily available inside torch vision. Then from torch vision's transforms module, we are going to import two tensor to convert the images into tensors, so that our machine learning model or deep learning model or neural network can understand the numbers basically. Then matplotlib for plotting purpose. And finally, as you can see, we are running on CPU shown here. You can see, right, it's connected, the resource and all those stuffs. And yep. So fashion MNIST dataset, you already aware that fashion MNIST dataset contains images that represents objects or basically clothes and all those stuffs. So different stuffs. It has a multi-class classification data structure. Okay, the data is mostly in grayscale image, and it contains 10 different kind of clothing items. Okay, so this is the overall dataset, how it looks like. Okay, it contains bags, shoes, t-shirts, hoodies, and all those in a grayscale image in a 28 cross 28 pixel in one color channel. That's your gray channel. Okay, so I hope you already are aware of it, and if you are not, you can directly go here in the fashion MNIST page, this page, and you can read more about the data. Okay, and we're taking it from this datasets module. So yeah, to download it, we need to provide the following parameters as mentioned here, right? We need root. So that will be the root directory or path where the data will resides. The train boolean parameter, so whether we need training data or not. Okay, transform function or transform that can take the PIL image. So what we are getting PIL image from the function, basically this fashion MNIST. When we are calling, we are getting PIL image, so we need to convert it into tensors, right? So some kind of transformations need to be done. Then your target transform, if it is if you are doing anything in target set, then your download, whether you want to download the data set from internet and store it in disk or not. Okay, So if you see what we are doing, we are just setting the training data object, and for training data we are calling the data sets as we have imported it from torch vision. We are calling the data sets, and then we are calling the fashion image function. Inside we are providing all the parameters. Okay, we are not providing any target transform. Okay, that means our levels we are keeping it as it is. Then our transform, we are mentioning this two tensor function that we have imported from transforms module of torch vision, and that's it. That is our train data, and it will get downloaded when we run the cell. And for testing data, what we have, we are doing the same, mentioning the root. Then we don't need training data here, so training equals to false to get the test data. Then download equals to true, and transform equals to tensor. And we don't need, for testing we don't need any kind of transformation for target, right? So target transform, we are not mentioning anything. So if you run, you will get something like that, and then the data will get downloaded. And once that is done, then you have the images with you, right? So this first thing, it will come to top. Okay, so once that is done, let's just take one training sample, how it looks like. So we have the training sample in training data in this object, and test sample in test data in this object. Let's just bring the variables. Okay, and let's just start running it. Okay, so it's done. Yeah, now if you see your image and levels, and these are the two things available inside your train data. So you can see this is the first image, how it looks like. So it's nothing but a tensor, as we have used this two tensor, this one, right? So if you don't use that one, you will get a PIL image, as we have mentioned this function to transform. So it gives you a transform tensor thing. So you are getting a tensor. It has it has definitely 1 2 2. So if you count, you will find 28 cross 28. So I'm not counting how many rows it has, I'm just counting 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8 3 8 24, and 4 is 28. So if you see, it has a 28 cross 28 pixels. So each pixel corresponds to one numerical value that you can see here. Okay, and that's same thing you can see in the variable. Let me just इसको थोड़ा सा छोटा कर देते हैं. Yeah, okay, so we'll just close this one, and in the level section if we go, you will see nothing but one level. Let me just call it, and you will see it has a corresponding level of 9. And we are not doing any kind of transformation, that means any one hot encoding or something like that. So it is just giving us the raw level value, that is 9 as integer. Okay, now let's just print or visualize the image in an image format, as it's a 2D image. For that we are going to use matplotlib, and first we are going to use the image object and squeeze all the unnecessary shape. So why we are doing this, as you can see, this code is important here. So if you just move this upward, you will see, if you do a shape, you will see it is 1 comma 28 comma 28. So this one is just to mention the number of channels it contains. That means it's a gray image. So if you do the image dot squeeze, it will just squeeze this one part. You will have a 28 cross 28 matrix or tensor. And once that is done, then you can use image show, show this function to plot the overall stuff. Okay, so let's just cut this portion and only run this portion. So what went wrong? Okay, I didn't run this one, right? Sorry. Okay, and now if I just run this one, I will see, you can see this image 2D, it's nothing but a tensor, but it has a different shape, right? So I can also confirm that image 2D. Okay, let me just, now you can see this is the image, how it looks like. And for this title axis and all those stuff I'm printing, so you can see the level also in the title. The level is 9, right? And now if I do image 2D, okay, image 2D, and I print, I will see image 2D dot shape, and I will see it will be 28. Let's say shape, the image dot shape. You can see the one got removed, right? That's why you will use this squeeze function. Now yeah, that's gone. Now come to the modeling part, right? So your data is ready. Okay, your data is in tensor format, your data is ready. Now how you have to understand how to build the channel, or how to prepare the data, or how to prepare the model. Okay, so first is the data part, and data part is almost ready. And what you have to understand, key normally in PyTorch your data goes with along with batches, right? Because when just imagine you have millions of data, right? You cannot feed all the data at once, or you cannot feed one sample at once, right? So mostly we use power factor of 2 as batch size. So we'll just bundle up 10, 20, 30 samples together, and then we use that repeat numbering for sampling, and we feed that into the channel, or basically into the model. So here the common batch size is 32, can be anything ranging from 32 to 512. That's the standard one. And how to send, and normally how the format looks like, that you have to remember. For PyTorch it's NCHW for any image. Okay, so 32, I mean N is stands for your batch size, C is the number of channels. So let's say instead of gray you have normal pictures or normal images, right? Then your C will be 3, so it will be 3 comma 28 comma 28 instead of 1 comma 28 comma 28. So that one thing, this thing is very much important for any image classification or segmentation that you are going to perform. Okay, and once that is done, you have this two, right? This train data and test data available with you. Okay, so what we can do, we can check the length, how much data it contains. So length of this train data dot data. So here you can see it is nothing but a data set fashion units number data points, right? It contains 10,000 and 60,000 root local. So the location, the data split, okay, what type of transformation it has done, all this information contains inside this object. So if you call train data dot data and length in top of it, you will get the length. Okay, so here you can see we have 60,000 for training images and 10,000 for testing. And for class names, what we required train data dot classes. That will give you the name of classes. So we have ankle boot, bag, blah 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 stuff. So it's total 10 thing. So one thing that from this understanding of the data we can get, or we can understand, that we have image classification problem where in training you have 60,000 tensors available now with you, 10,000 tensors for testing that is available, along with the labels, and the label contains 10 values. Those 10s are ranging from this ankle boot to t-shirt. So it's a multi-class classification problem. Okay, now here in this code what we are doing, we are just manually printing all the available objects, basically based on their labels. So this is a random plot, 4x4 plot that has completely random 16 sample, just to show what the data set looks like. Okay, the code is similar to the previous one with only for loop. Okay, now first thing, as we have mentioned, this tutorial or this video is particularly about understanding this data loader, data set and transforms, how it works. Okay, so first thing, to load this data, this tensor, basically will be requiring torch.utils.data.DataLoader. Okay, or DataLoader for short. Okay, so why it helps, or why it requires? So it helps load data into a model for training and for inference. So for both the stuff we will be requiring the data loader in object, basically. Okay, so what it does, it turns a large data set into a Python iterable for small chunks. So that's what I'm mentioning, right? For training any deep learning or machine learning model, you will be having very large set of data. So to train those, you need to chunk those in a bundle of batches that we have mentioned. The batch size will take care of it, right? And these smaller chunks, you need to iterate over the smaller chunks to complete one complete epoch or iteration, right? So there this data loader will help. Okay, the smaller chunks, as I have already mentioned, it is termed as batches, and the only parameter for batches is batch size. That can be multiple of 2. So normally we start with 32 and we go up to 512 or 1024 based on what gives us much more performance. Okay, and it affects the learning in the optimization part. So the optimization and batch has a bit relationship, how it will learn. Okay, so why we require these batches? Because it is much more computationally efficient. Okay, in any ideal world, when you are doing some forward pass and back pass or back propagation across all the data at once, okay, it is impossible to track all those computations. It will become very much expensive, and I practically don't think for larger data any computer supports that kind of in memory fitting. So that's it, that you have to only understand. And as I have mentioned, the 30. Yep, now let's see. You have your batch size defined as 32. Now you have already defined your train data and test data there, right? So we'll use this data loader to load the data set and to turn our data set that we have available in our disk, and we'll make it as a iterable Python iterable. So we are calling the data loader from torch.utils.data module. We are calling the data loader function. We are passing the train data, that means dataset instance. We are passing the batch size, that is 32, and for training purposes we are shuffling the data. Shuffle equals to true. For testing we are not shuffling the data. Okay, and once we'll do that, you will see, and we'll just print, you will see all the data loaders. All the data loaders will get stored as a Python object, and you can see the length of training data loader is 1875 for batch with batches of 32, and for test it is 313 for batches of 32. So if I quickly bring my calculator here and I multiplied 313 with 32, I will see it's 10,016. That means in our last iterable we have 16 data set or 16 samples there, right? So that's how your data loader loads or creates one iterable on top of your data set, and your data set is nothing but small batches of your data samples. Once that is done, okay, how we can iterate over any iterable objects in Python? We will call this iter built-in Python function, and we call the next, and once we'll call, it will load the first batch that contains 22 sample. Each sample is nothing but one image, that is your 28x28 grayscale. Okay, so that thing we are storing in your this train features batch and train label batch, and these are the shapes. So for levels also we will have 32 samples and nothing but scalar samples that will contain values like 1 2 3 4 5 6 7 8 9, something like that, right? Okay, now once our data is ready, data loader step completion means in PyTorch your data is ready for training. So what you require next, you will be requiring the basic models, loss function definition, and optimizer. Okay, these three things will be required. So for building any linear model, as we have already seen in our previous videos, nn.linear, that layer, and as it's an image data, that means it contains 28 cross 28 pixels basically. That means it will be a 2D mesh or 2D array. We need to convert into basically flatten vector or flatten data or flatten tensor basically. So to do the flattening thing, so that our network can learn, we will call this nn.flatten. So you can see here, first we have to flat our data. So for that we are calling nn.flatten, and once that is done, let's say we are taking first example, and we are passing the first example in this flatten model. So this output will give me one shape that will be 28 cross 28, that means 784, and once that is done, we can print the shape, and you can see it, the previously it was 1 28 28, and after that it is 1 784. So now we are in the model building phase, in the model building layer. As you can see, we have already shown in the previous videos, right, how to build custom PyTorch machine learning models. So we'll pass nn.module. This will be our parent class for building any neural network related utilities. So we'll call, to use this one, we'll call this super.init, and in the constructor we are passing the input shape, the hidden units, and output shape. These three things will be required to define your linear model here. So first we are going to apply one sequential linear layer. So how it will look: neural network linear layer. So here you can see this will be the network looks like, where we'll have some input, then we'll have one hidden layer, and for that layer we'll be requiring the hidden units and output shape. So these three things will be required. That three things we are passing: output shape, hidden units, and input shape. Okay, so first we'll do the flattening to flatten out and make the 28 cross 28 grid to complete 784 feature, and then we will apply one linear transformation or linear layer, where the input will go and the output will be the hidden units. That means this portion, this is the first layer, and in the second layer, what will be the input? The input will be the hidden units, and the output will be the output shape. And once that is done, we are just calling this layer stack object, and we are passing the input. We are just providing the data, and that's our computation forward method will get implemented. Okay, So that's our very basic model. Okay, so there our input shape is 784 feature vector. Our hidden unit has 10 number of hidden neurons, and output shape will be length of class names, that means 10. And class names, if you forgot, I'll just quickly forward upon, this is the class names object. Okay, so now that's done. What we are going to do, one manual seed so that you can replicate the same behavior as I am getting. We are calling the class, we are just creating the instance of the model with the parameters. We are passing 784 as input shape, 10 as hidden units, and output shape equals to length of class names. And once that is done, we are defining that this model, we particularly wants it to in the CPU, as it's already in CPU, as our by default device is CPU, and when not training it, the tensor or data tensor is not storing in GPU. So definitely this portion you can write or don't write, not a big deal. So you can see it's nothing but a sequential layer stack, where your first you are doing flattening, then you are doing one linear layer, and the second linear layer will provide you the output. And once that is done, we are just creating one helper function for plotting and all those purposes. Okay, so to see the content, you can go here. So I have taken this example from Coursera, so it's already there, the example. You can see the code, what are the plots. Okay, train timing print, then accuracy calculation is there, then prediction plots are there, then there is one function for decision boundary. Okay, these are some of the helper functions on top of, I mean, by using those we are going to build some what prediction values. We are going to plot some confusion metrics and all those stuffs, and the learning stuff, so that I mean the codes will not be too much for this. Now next we are importing accuracy function from helper function. So if I go and see what's this accuracy function is doing, control F, accuracy function, you can see what it is doing. Okay, it is checking whether the true value and predicted values are equal or not, and if it is whatever equals, it is doing the summation, and it is storing the sum value as a scalar in this correct, and finally it is returning the percentage correct. That's what it is doing, this two line, right? That's what this function is doing here inside this accuracy function. Okay, and in loss we are defining the loss as cross entropy loss, and we are defining SGD with a learning rate of 0.1 for optimizer. So for optimizer we are using torch.optim.sgd function. So from optim module we are taking it, and for losses we are taking torch.nn.cross entropy losses. Okay, now our loss is ready, our optimizer is ready, and our model is ready. And this is one short function they have created for timers, how much time the training will took, just to compare the training time required in CPU versus GPU. So I'm skipping it for this video, it's not required. So now let's say we are doing it for 3 epoch the training. So for every epoch, you can see first we are printing the epoch length. Here you can see the first epoch will get print for every epoch. Then first you are defining, so there will be model.train that will define, okay, this is right now in training mode. In PyTorch you can define in that way, so that you cannot mistakenly run any inference inside of training, or evaluation inside of training. So we have our data loader for iteration. So we are just taking the batch, the data or feature, and the levels from the data loader. And first we are passing, there's 5 steps that I have already mentioned in the previous lectures and classes, right? There are 5 steps you have to follow for your PyTorch machine learning. So it will be same irrespective of your problems mostly. So first you will do the forward pass, and once the forward pass is completed, you will get some output. From where you will get some output, if you see the image right here, yeah, you will get these outputs, right? No matter, because by random, when you are defining these neurons, you have some random values inside this neuron, right? So you have some output, and then you can calculate the loss using loss function that we have defined here, which is nothing but your cross entropy loss, right? This one. Then we are accumulating the loss per epoch. Okay, and then what we are doing, we are making, first we are just deleting all kind of gradient values that the optimizer produces. Then we are starting or doing the backpropagation or backward differentiation and calculation based on the loss value. And once that is done, we have the upgraded version, or we have the step counts with us. We are calling optimizer.step to update the weights and biases. And once that is done, for let's say I'm reaching 400 samples, I'm just wanted to batch, and as well as you can see how much batches I have completed, right? So here the first thing, what you have 60,000 of samples, right? So as you can see, first at the very 0th sample it is looking, then it is 12,800 sample it is looking, and in that manner it is going on. Okay, so as you have seen, we have 1,800 batches, right, for training. So mostly it will print five samples, right? 1,800 was the number, right? Where it was there, 1,800 is the number, and 313 for test, right? And same, once that is done, what we are doing, calculation of the test matrix and train matrix needs to be done. So once that is done, divide the total train loss by length of train loader. That means average loss per batch per epoch we'll get. So this what we are doing, we are doing the accumulation here, right? Here we are doing the total loss accumulation, and this loss will be accumulative. Accumulation will happen for both the for loops, right? This for loop as well as this for loop. So this loss will be for all the epoch and for all the batches. So if you divide it by the length of train loader, okay, then you will get average loss per batch per epoch. Okay, so that will be your training loss. And same thing with the model.eval mode. When it is on, by keeping this function on, we will perform the same inference. So the code is little different. So here you can see we are just using one with clause, and here we are mentioning this flag. Okay, here right now the mode is inference mode, and for every x and y in our test loader, first we are doing the prediction, then we are calculating the loss, we are calculating the accuracy using this accuracy function from the helper that we have just defined. Then again same thing we are doing with the loss, we are calculating the average loss based on the test loader, and same thing we are doing with the accuracy. And once that is done, we're just printing out the accuracy, training loss, and test loss. So here you can see this is for first epoch, our train loss is this per batch, and our test loss is 0.5, and our accuracy is 82%. For second epoch, or the second round or second iteration or first epoch, I can see for training the loss is getting reduced, for testing the loss is getting reduced, but accuracy is also increased slightly with the linear model. Here also for third epoch, you can see the training got again reduced, but it did not reduce the test loss that much. That means accuracy will not increase that much. Okay, and finally you are printing the time, how much time it requires. Okay, now for prediction, whatever we have just done, right, this phase, okay, this portion of code, testing code, let's just make it as a function so that we can again reuse it. So that thing we have done here, we have just made one eval model, and then we just call the eval model, we'll pass the model and the test data. So loss function and accuracy function, and finally if you print in a dictionary, you will get the model name, what is the loss value on test data, and what is the accuracy value on top of the test data. So I hope till this no one has any concern, or you guys are aware. So now to make this code device agnostic, we'll just search for CUDA. If it is available inside, then we are going to use the CUDA, that means our NVIDIA drivers or GPU for testing. And if it is not available, we are going to use CPU by default. Okay, so that's how you will build platform agnostic PyTorch code, just to